1 o'clock on Friday the 5th of February. It's a big day for Ilka Jahn. We have gathered here to listen to the public defense of her thesis. Quite often I say welcome to a barbecue party, because sometimes it becomes very hot here, especially for the respondent. But today I think I say welcome to the Viking party, because we woke up this morning with -10 outside, and Ilka has totally adapted to the Swedish situation, so she's preferring to have the open window to the outside coldness. So welcome to the Viking party today. So, on behalf of KTH, it's my pleasure to welcome you all physically and online to this public doctoral thesis defense within the field of electrical engineering. My name is Mats Leksell, and it's my privilege to be the chairman of this public defense, and I will guide you through the official procedure of the defense. Practicalities, we are broadcasting it as a webinar. However, if there are any technical problems, please phone me on my mobile, and I know that we have many attendees that has my mobile number and you can phone me. So, I hereby open the public defense of the doctoral thesis entitled Protection for Multiterminal HVDC Grids, a Digital Contribution. The respondent is Ilka Jahn. She has made her research here at KTH under the supervision of Professor Hans-Peter Nehm and Associate Professor Staffan Norga, somewhere in the room at least. Apart from Ilka, we have the main person, which is the opponent, Professor Dirk Westermann. Are you here?
Yes, I'm here.
Well, welcome. Thank you very much for acting as opponent in this public defense. And then we have a grading committee that consists in the order of geographical distance. Professor Soledad Immaculada Bernal Pérez from the Politècnica University of Valencia.
Hello.
Very welcome.
Good morning.
And we have Professor Oriol Gomis Bellmunt from the Politècnica University of Catalunya.
Hello, good afternoon.
Hello, welcome. And we have Professor Tim Green from Imperial College in another time zone, but he made it.
Yes, good afternoon, everybody.
Very welcome. And then we have Docent Nathaniel Taylor.
Hi, good afternoon.
Nathaniel?
Yep, good afternoon. Do you hear me?
It's a bit weak, but we can hear you.
Okay, yep, I'll move near it. I can't turn on my video, but you can let me later.
Oh, sorry, I'll do that later. Absolutely. So, the procedure of the public defense is as follows. First, I will give the opportunity to the respondent to comment if there are any formal errors that you would like to bring up. And after that, you will make your presentation.
There's nothing I want to bring up.
All right, thank you very much. After her presentation, Professor Dirk Westermann will make the opposition. So he will discuss and scrutinize and comment your work, and you have the possibility to respond to the remarks from Professor Dirk Westermann. After that, I will ask the grading committee to put their questions that they would like to put to you. And then finally, I will open up the screen for the public also to put questions. And you do that via the Q&A that we have in this webinar. So, with these words, I would like to give the screen to you, Ilka.
Thank you, Mats. Dear Professor Westermann, dear members of the evaluation committee, dear small audience here in the room, and dear audience on Zoom. Thank you all for joining my PhD defense. The topic is Protection for Multiterminal HVDC Grids, a Digital Contribution. And in the next 35 to 40 minutes, I'm going to give you an overview of the work I did in the last 5 years.
The screen is yours, Ilka.
So the idea is still to exploit, thank you, Mats. The idea is still to exploit renewable energy from offshore wind in the North Sea. So to do that, you have to build an offshore wind farm and you have to connect it onshore. And one way of doing that is by using high voltage direct current or HVDC systems. Now, there are several countries surrounding the North Sea. So it's not only one of these point-to-pointings that is appearing, but several countries surrounding the North Sea will do the same. And here we can see blue boxes, and these boxes indicate something called a converter station. And here you can see what such a converter station looks like in the field. So it's the yellow big platforms in the background. And if we zoom in, you will notice that this is actually, now let's hope this is working. This is actually a several-story building, and on top of here you can see, for example, 6 containers. So this is a very large construction, and it's not straightforward to build it offshore. That's expensive. And then the second thing that is expensive is also the actual converter hardware that you have to put inside. So if I move back here, the idea, instead of having several of these platforms, is instead to combine them into one platform. And by doing that, you build an HVDC grid. So this is still a very simple HVDC grid, and it results in cost savings for the converter stations and in reliability improvements. And by reliability improvement here, I mean, for example, if UK can't take in all the wind energy, then instead you can transport it to continental Europe or vice versa. And even if there's no wind blowing, you still now have a connection between UK and continental Europe that you can use for energy balancing or trading and so on. And then ultimately these infrastructures would evolve into a more complex grid. But there are no HVDC grids in Europe today, despite there being early patents in the 60s and 70s, several EU projects, and HVDC grids actually being built and put into operation in China right now. And to be fair, the last 2 points didn't apply 5-6 years ago when this PhD project was planned and started. And back in 2015, one concern was the HVDC grid protection. And this is a question that addresses what happens if you have a short circuit somewhere in the system. What do you do with this HVDC grid? And the idea and what the idea is in my PhD as a reference is to disconnect the faulted part and let the rest continue operation. And I looked into that topic in the last 5 years, and there's not like a singular contribution, but I addressed this topic from different angles. So the main objectives of this PhD are 3. The first one is to provide suggestions for feasible solutions for field implementation. The second is to enhance the understanding towards a more straightforward design of the HVDC grid protection. And the last one is to increase confidence in the technology and develop solutions. And I did that, or I addressed these objectives by doing 3 things: literature reviews towards feasible solutions, suggestions, simulation studies addressing the design of HVDC grids, and the third one is lab studies to increase confidence. Because back in 2015, there were actually very little lab results for the HVDC grid protection topic available. And then in academia, you count contributions in terms of publications. So here you can see the papers that you also find in my thesis, classified in these 3 categories. And in my presentation, I'm going to start from the left, go through the right, so starting from introduction literature review over the design aspects to lab studies. One thing here is some related publications that were actually first authored by the project partners, but because they were using a prototype that I developed in my PhD, I think the results are relevant and interesting to show. And then there's also a topic that goes beyond the actual HVDC grid protection topic, and that's a proposal for open source HVDC control and protection, which I find very interesting, and therefore I'm going to mention that as well. Now, but going back to this HVDC grid here, now I added one more line diagonally, And if we keep this structure in mind, I translated it into a simplified circuit diagram. So here we have 4 converter stations, 1, 2, 3, 4, and these are connected by cables of different lengths. And using this example, I'm going to explain what I mean by HVDC grid protection. So the reference idea I'm using here is so-called fully selective protection. And for example, if we get a fault here on this cable, this diagonal cable, the first thing that has to happen is that this fault has to be detected. And this is done with an intelligent electronic device, or IED. And this is a device that a few years ago you would have called a protection relay. So this device takes in measurements, and depending on an algorithm, it will then send a trip signal to open a DC circuit breaker. Now here you can see an example of what such an IED looks like in an industrial prototype. So this is an industrial HVDC protection IED, and it's approximately the size of a fridge, just to give you an idea. And then the DC circuit breakers, that's all the red boxes here indicated. That's actually a bit larger. So here you can see a picture of a full-scale HVDC circuit breaker. That's basically all the equipment here in the background. And again, the idea is to disconnect only the faulted part, and the rest continues operation. So here I've only drawn one IED and the respective measurement equipment, but obviously the same would be installed at the other line end and at all line ends in this grid. And now that I'm already talking about the infrastructure that I haven't shown, I just very quickly want to mention the HVDC substation communication. So if we take this substation again with several IEDs for each link, then if we zoom in, it looks, for example, like this. And for backup protection purpose or busbar protection, it makes great sense to let these IEDs communicate. And just to keep it short, this has to happen fast, reliable, and deterministic. And one way to do that is by building up on Ethercat protocol. And for the sake of time, I'm not going into detail here, but I refer to publication number 3. But going back to the actual IED and what it's doing. So inside of this IED, there's a mathematical equation working that's called fault detection algorithm. And fault detection algorithms in this context can be distinguished into single and double-ended algorithms. So what is shown here is a single-ended fault detection because it only looks at local measurements. And if instead this IED had another input with communication and information coming from a remote line-end IED, then you would call this a double-ended fault detection. And in my literature review, I argue how a combination of those two makes sense in a field implementation, especially for long cables. But for the rest of this presentation and also the remainder of my PhD, I only looked into single-ended fault detection. And the most prominent algorithms mentioned in literature, just to mention them here, are TVDT, the IDT, traveling wave, and then undervoltage overcurrent, which is very familiar from AC protection. Now, one important aspect for the single-ended line detection is the DC reactor to define the protection zone. And I'm going to explain what this means with an example again. So if we take this internal fault here, then the measurement and fault detection up here has to be able to distinguish this internal fault from an external fault, because for an external fault it's not supposed to detect it or trip, and the only electrical differences in between are these line inductors. So the sizing of those becomes important for shaping the actual physical signals that are then fed into the fault detection. And I'm going to come back to that line inductor sizing later. One more high-level comment I want to give is the requirements on the protection in terms of reliability. And again, if we have a fault here, you have to have certain positions in the grid that's on this protection zone, and not shown down here, they have to trip. So those responsible for that protection zone have to trip, and then everybody else, every other position in the grid should not trip. And if I keep these very simple terms, have to trip or should not trip, and translate it back into the actual fault detection algorithm, it looks approximately like this. So for every position in the grid that has to trip and has to detect a fault and open the circuit breakers to disconnect the faulty part, we have an algorithm, and here I divide by threshold, so I normalize, and then usually the algorithm output is close to 0, and then once a fault happens in the protection zone, this signal goes above threshold. So here the trip happens at 1 per unit because I normalized the threshold. And then similarly, for every fault detection that's not supposed to trip, should not trip, for a fault happening, you might see a bit of a disturbance on the signal, which is completely okay, but it should not get anywhere near the threshold. And note here how I have indicated a gray area, which is same here, which is called protection margin. And the reason why this is important is because you don't want to design the fault detection such that it goes above threshold by like 1 to 3%, because if any of the equipment in the field is not behaving exactly as you assumed during design, then the protection system is not going to work. So that's, for example, manufacturing tolerances, aging, or things that you just didn't think about. So you want to design the protection such that it really goes above threshold by like 30–50%. And same, everyone who should not trip should stay below threshold with a really nice buffer. So the margins account for parameter uncertainties and changes, modeling inaccuracies, and you can argue in HVDC protection also lack of experience. And here I end the introduction and the overview of what I mean with HVDC grid protection. And holding this thought about the margins, I move into the simulation studies. So I investigated protection margins in an example. Here we have the Scottish Caithness-Murray HVDC link with future extension to Shetland. That's a real project. So it's, I think this is Caithness, this is Murray on the left, and then a star configuration with a future or ongoing extension to Shetland. And for the sake of research, compared to the actual real project, I changed 2 things. The first thing is that I added 3 circuit breakers and IEDs in the star connection, and I made it a multi-vendor setup. And the idea is that vendor A designs the left part of this system, already assuming the future extension. So these line inductors, these DCCBs, and the IEDs are already installed. And then a different vendor comes in and has to do the extension, but still fulfill the requirements for fully selected protection. So that part is done. The second vendor comes in, and now the question is how to design the protection. And what I did here is I investigated what happens if the vendor A cannot share a certain piece of information, for example, due to intellectual property rights. And I investigated a few different ones. And here I just want to show you one example. What happens if the vendor B has to design the HVDC grid protection and does not know what the vendor A installed as line inductor size here. So the assumption is, in detail, vendor B assumes 50 millihenries installed here, but in reality it's only 15 installed. And now I apply a fault in simulation here on cable 2, and a wave moves through this star connection to the measurement for the new vendor B's fault detection, and the arriving wave is much larger than expected because the line inductor in reality is much smaller than the vendor B thought, which results in an unwanted trip on cable 3, which basically means that Shetland is disconnected, although it was not necessary. And if we look into the fault detection signals in a bit more detail, you can see here on the x-axis the time, and on the y-axis the dV/dt fault detection. And this is again per unit normalized to threshold. So at 1 per unit we get a trip, or a fault detected and then a trip. And in dark blue we can see here how dark blue is the fault detection on the faulted cable, and that goes above threshold at time 0, very nicely, exactly as expected and required. So this circuit breaker is going to open on the faulted cable. There you can also see the red signal. That's the fault detection on the neighboring cable of the same vendor A, and that goes yeah, you see a disturbance from the fault, but it doesn't go near the threshold. And you can also see how it still has a certain margin to the threshold as required by design. But on the new link with the new vendor B, who didn't know the line inductor size, that one designed the fault detection as shown in turquoise here. And you can see here how it goes above threshold just by a tiny bit, but that's enough to trip it. And if the new vendor B had known the correct fault detection, line inductor size, it would have designed the fault detection in a different way such that it would have behaved as I indicate now. So here we would still have had a nice, okay, that you can't really see, a nice protection margin, and then with that knowledge, the link would not have been disconnected. And I iterated through several aspects, and what I find is that it's really necessary to share information about the line inductor sizes and thresholds in such a setup. There's lack of information that consumes quite a large portion of the margin. For example, the sampling of the fault detection consuming up to 50%, or the surge arrestor curve in combination with certain algorithms consuming 30-35% of the margin. And I didn't see a malfunction, but I mean, this is a warning sign if you just consume 50% of the margin by not knowing this kind of aspect. And then going deep down into the details of the fault detection, I find that the software filter used for fault detection is actually not that relevant for these kind of studies, or for the functioning reliability of the protection system. So the lesson is to use high margins and to share information. And one thing I want to mention here is that actually there are many things that I have not taken into account yet. So I have not yet taken into account the physical real parameter changes, and I have not taken into account several parameter changes, or a combination of lack of knowledge of different things at the same time. But you understand it's a very complex topic. There are hardware and software aspects involved, and this is just to give you an overview. And I promise not to go into detail, but this is just to give you an overview of all the different aspects that have to come together in software and in hardware, and how they impact in the HVDC grid protection. So I thought in my PhD, I did many studies on how one singular thing impacts on another thing, but I believe it needs a method to take all of them into account at the same time, and ideally also give you a design for an HVDC grid protection that is optimal. So for optimal design of HVDC grid protection, taking into account all of these complex interacting parameters, I want to show you an example, and as I explain this example, also explain the method that I developed for the optimal design. So here we're back at the 4-terminal grid I showed before, and just to make it a complex or a complicated problem, now I use 3 different kinds of circuit breakers with different opening times, and for example here you see them all on the same bus. And I have a requirement on fully selective protection. I also have a requirement on a desired protection margin, so that's an input to the method and to the tool, and then the tool has to ensure that I get this protection margin ensured. The third thing is I want to ensure that I stay below a certain maximum DCCB current, otherwise that device can't function. And then lastly, just to make it a really complex example, I don't want any of these 4 converters here to block so that you can still provide reactive power to the AC side. And from a protection viewpoint, it's to me, it's not really important how these things are fulfilled and achieved, as long as they are fulfilled. And that's why these go under optimization constraints. As long as they are fulfilled, I'm happy with the design protection system. And this gives me the freedom to choose a parameter as an optimization goal. And here, just as an example, I want to minimize the line inductors throughout the grid. So all of these, and actually I want to minimize the sum of line inductors. But if you, and this is just an example and you can change it, but if, for example, you know the most expensive component or the notoriously annoying component, if it's just too large, then you can change that. And then 2 more things before I go into the optimization is that in this method, I investigate a large set of faults because there's not a singular worst case fault for all the positions and all the involved things I have to design. And the second thing is that I use an embedded EMT simulation. The reason being a very dynamic system response with a lot of hardware and software parameters and aspects interacting, and the traveling wave aspects, of course. And I use a genetic optimization. Genetic optimization means that I input a population of possible solutions. So one possible solution for this HVDC grid consists of a range of line inductors for all of these line inductors here and the corresponding thresholds. And this is kind of offered as one solution to the tool. And I also feed in a large number of those. So the tool runs all the simulation checks if the optimization goal is approached and whether the constraints are fulfilled. And if not, the input population is updated. And genetic optimization means that you keep the best members, you take a portion of the most promising members and shuffle around their features, and then there's a portion with random mutation. And once the optimization goal, here that was the sum of line inductors, is approached, the tool finishes and gives me an optimal inductor size and threshold as a solution for this HVDC grid design. So coming back to this example, the goal was to minimize the sum of line inductors. And this is how the genetic optimization approaches this optimum as time passes. So on the x-axis, we have the generations that are being tested and how they improve. On the y-axis, we have the penalty value. That's basically the sum of line inductors. And you can see here an initial starting point, summing up over all line inductors here, that's 20 Henry. And that's quite a large value, but it's very hard as an initial input, as an engineer, to find a good solution that fulfills all the requirements. So keep in mind here, I want to achieve fully selective protection, protection margin of a certain percent. I've chosen plus minus 50% here. I want no converter blocking, and I also have to take into account the maximum DCCB current. So that's not straightforward to design by hand, but applying the tool to this initial guess, I can observe how the optimization gives me a solution with a 71% decreased total inductor size. And this is just possible by adopting a software setting the thresholds in a smart way, while still ensuring that all the other constraints are fulfilled. One last thing is you can see 2 curves here, and that's more for someone who's interested in the optimization. The red one is the best member of this population, and the blue one is the mean penalty for the complete population, and you can see how they are approaching, and that means there's not much happening in terms of improvement anymore, and that's why the optimization stops. And now that I've shown you how you could design an optimal HVDC grid protection system, I want to move to the lab, because I mean, you've seen It's a complex topic. There are a lot of things you have to take into account, and nobody would install such a complex large grid full scale in the field. So one intermediate step you have to do is to go to the lab and test some of the solutions and prototypes of different degree. So what I did is that I developed an open source protection IED. And as I mentioned before, this prototype is used for the fault detection. The design is available for download on KTH GitHub, hardware, software, and a building manual also. And what it can do is, as I said, fault detection for meshed HVDC grids, and the implemented algorithms include the DVDT, traveling wave, overcurrent, undervoltage, and busbar protection. Here you can see the graphical user interface that you can use to connect to the IED with all kinds of settings, with a window where you can read out the IED transient fault recorder, a window where you can estimate the fault detection signals compared to threshold, so basically the margins, and then also a window where you can see the IED fault detection times for different algorithms. And that's what the hardware looks like. So it's established off-the-shelf main board with some custom add-on boards to connect to the simulator, which we're going to see in the next picture. And that is what it looks like in the prototype in the box. So for testing, lab testing, we connect this IED to a real-time digital simulator. And such a simulator, that's this one here, can then model and simulate a European HVDC grid in real time. And the nice thing is that you can apply and simulate as many faults as you like and feed those to the IED, observe how it responds, feed it back, and then also have a look at how the rest of the system responds. And one of the early testing was done in KU11 Energy with the project partner. So this is my colleague Gareth Shafee, and you can see in the back how there are 1, 2.5 racks. And here you can see a very early version of the IED, just consisting of a board basically. And one very early test is to test with a very easy to detect fault. So here we have a substation with 3 outgoing lines, and we applied a fault to ground with 20 kilometer distance on the first line. And that's quite straightforward to detect. So again, in the first window, we see the IED transient fault recorder, and it's covering the complete substation. So here we have scale to real system value 320,000 volts. And at this point, you see how in dark blue, the voltage on the faulted link collapses. You can also see how at that moment in time, the current is rising in this link, and then a DCCB opens and this line is disconnected. In the second window, you can observe the fault detection signals as compared to threshold. So for example, here we get a really steep DVDT, and this DVDT is shown here. And then you can compare it to a threshold and investigate the margins. And third window shows here that there were 3 algorithms active, all resulting in similar fault detection times. And the next step then is to do that systematically. So Gareth Shafee did that in a study published down here. And what happened is that a fault was applied on line 1 along the complete line length. And what we observe is the IED operating time. Now, the reason why we did that is because 5 years ago, there was still this idea around, is it actually possible to implement these fault detections in a device? Maybe they are too computationally heavy. Is it going to work? Is it going to be fast enough? And so in this study, basically, we showed that it's fast enough, and this device is actually really fast. So on the x-axis, you see distance in kilometers, and on the y-axis, you see the IED operating time in microseconds. And this IED operating time is measured from a 5% voltage deviation at the measurement point until trip output high at the IED output. And you can see how for very close faults, the detection is around 100 microseconds here, and then for faults that are a bit farther away, the IED operating time is a bit longer, and that has to do with for faults here that travel through the cable, the steep voltage collapse is dampened, and that's why it's a less dramatic DVDT and it takes a bit longer to detect. And we also investigated several scenarios for high inductance, low inductance, and several algorithms, but it's basically the same trend. This is the maximum IED operating time. Here you see the mean IED operating time. There's a 10 microsecond difference, and this is easily explained by the fact that the IED is a sample system at 50 kilohertz with a 20 microsecond resolution, so you get a variability of plus minus 10 microseconds, which is exactly what you see here. And this is a generic test system, but the next step then is to go to an industrial test system. That is a bit too fast. And here we're back at the Caithness-Murray-Shetland 3-terminal system. And what you can see here are the simulators in the National HVDC Centre in Scotland. So that's an industrial test centre, and their task is to de-risk ongoing and future HVDC projects in Scotland. And they have, as you can see, a very large computation power and also access to industrial grade control and protection systems. And here I just want to summarize two publications, and the first one is authored by Mian Wang from KU Leuven, and this is a fully selective setup. So that's the same link that we've seen before, so Caithness-Murray and the future extension to Shetland. Now I put it down here so it fits on the slide. And there are 3 DC breakers here, simulated in the real-time simulation with 3 respective IEDs. And in this test, we had 2 physical IEDs connected to the real-time simulation, the one that I developed in my PhD, and the second one in industrial grade prototype from Mitsubishi Electric. And the purpose here was to investigate what happens if you have them in different positions, one line and the one IED, other line and the other IED, backup, and so on. And just to keep it short, all the tests worked, and for more information, I refer to the publication. But then another study I want to mention is a partially selective study, looking into only one IED installed and one DC circuit breaker, of course, simulated in the real-time simulation. And that's an interesting study because that's closest to what you would do if you're a transmission system operator. So instead of installing 3 DCCBs, it's likely that you want to install only 1 DCCB, and that's why this kind of study is interesting. And here you can see the IED fault detection. And sorry, let me go back. And what we investigated here is different combinations. So we had 2 DCCB models verified by the project partners, a hybrid DCCB representative of the ABB breaker and a mechanical DCCB representative of the Mitsubishi breaker. And then we had 2 physical IEDs to connect in the loop. Again, the one that I developed and the one from Mitsubishi. And we just iterated them so you get 4 different combinations. And it's the same behavior as before. We see on the x-axis a distance. This is a combination of the open source IED with mechanical DCCB from Mitsubishi. And on the y-axis, you see the IED operating time, which is similar to the values we've seen before. And it looks almost the same also for a different DCCB and for the other IED. So to keep it short, again, several combinations work. So several combinations of IEDs and DCCBs fulfill the functionality to achieve the protection performance we want. And the last part about the protection topic is it's actually field testing. So for that, we have to keep in mind that all the testing before is done on a real-time simulation, and that means that an engineer has to program that simulation. And that can come with simplifications, aspects that just have to do with the how you program the actual program, maybe computation power that is a limiting factor, sampling, and so on. So it's a nice thing to complement these results with field recording tests. And we were very lucky in the project to get field recordings from a fault in an operational HVDC link. And this is a very simplified diagram of that link. So we have a land station, a platform with an offshore wind farm, and then a fault happened on the negative pole close to the land station in a cable joint. And here you can see the fault recording from the actual link in the field. And what you can see here is how the negative pole voltage really nicely collapses, very clean. And then the same happens a few, half a millisecond later at the platform. So, and that delay is simply due to the fact that the traveling wave has to travel through the cable, and that's 200 kilometers long. On the positive pole, we can see how the voltage increases, and this is a symmetric monopolar system. These are the current measurements going up to 2.5 kiloamps. And so what I did is that I took these measurements, baked them to the IED, and observed the margins and trip times. And in a short summary, the device could successfully detect this fault with several algorithms and similar fault detection times, but different margin depending on the configuration. So just to give you an idea, this is the fault detection algorithms normalized to thresholds. So the trip happens at 1 down here. At time 0, the fault happens. And here we can see how different algorithms go above threshold with a different margin. But again, this is a complement to the systematic real-time testing and also further increased confidence in the previous developed ideas and solutions. So that was my what I wanted to say about HVDC grid protection. And now shortly, I just want to mention the proposal for open source HVDC control and protection, which goes a bit beyond the actual only protection topic. But to recap, at the very beginning, I motivated why it's important and necessary to share information in order to get a reliable multi-vendor HVDC protection. And now for control, there's actually a related topic. So what people observe in the field is control interactions, unwanted interactions. And what you have to keep in mind with these unwanted interactions is that today the HVDC control and protection is inherently black box, and that's simply due to intellectual property rights of the vendors. But that's coming with, say, complications. If you, for example, wanted to build a point-to-point link with 2 different vendors, vendor 1 here and vendor B, vendor 2 there, and the control systems are not tuned to work with each other, because they are black box and you can't look inside and then tune them, it's very likely that you get an unwanted interaction. So you might argue, okay, but then we build one link, only purely one vendor, they know everything that's going on, you can control and tune the control and the protection exactly as you need, and it works. And then another vendor can do the same, and there's no need to make it open, make the control open. But then if they are electrically close on the AC side, still there's a potential for unwanted interactions, and then we're back at how do you solve that if you can't investigate the problem because the control is black box, and then how do you modify it in a multi-vendor setup? So and then the same also if you at one point connect on the DC side, same story here. So the idea is to use an open source external control to partially overcome these possible interactions. And very simplified, how this could look like is shown here. So closest to the actual control we have, closest to the actual converter hardware we have the gate signals and a closed internal control done by the same vendor that manufactures the converter. And that makes great sense because that's really concerned with what's happening inside of the converter, and this is about pulse width modulation, cell balancing, arm balancing, energy balancing, circulating currents, and so on. But to make it easier to overcome multi-vendor interaction issues, the idea is now to have an open source upper layer or external control, and that would cover the control layers that are mostly concerned with the external behavior of the converter, such as power or DC voltage, and maybe even the current control. And then the question is where to make this cut, and then also how to do this interface. But to summarize the contributions in my PhD, I want to say that I have contributed with suggestions towards practical solutions in the field. I have contributed with a method for a holistic and optimal and automated approach for design. I have increased confidence through developing a prototype and many laboratory studies. And then lastly, I have suggested an open source HVDC control and protection. Future work, in my opinion, should focus more on the margins in the HVDC grid protection, have more focus on automatic testing and also bringing the time down in automatic testing. And then lastly, not only focus on the control or the protection, but combine those ideally in an open source structure. And here I'm at the end of this presentation, and I want to thank the Promotion Project and the European Union for funding, and colleagues in the project for very nice collaboration. And then I would like to thank you all for your attention.
Thank you very much, Ilka. A very thorough presentation of your work. Although I'm afraid that the opponent will probably have quite a lot of questions still, regardless of this very thorough presentation. With this version, I would like to give over the screen to Professor Dirk Westermann to make the formal opposition on your work. The screen is yours, Dirk.
Yeah, thanks a lot. Hope you can hear me.
Yes, we can hear you loud and clear.
I also switched my video on, so at least my camera is operating here. Yeah, thanks a lot for this very excellent presentation. It already answered some of my questions on the thesis, but I still have some, of course, and I will ask them in the same sequence you have chosen for presenting the results of your thesis, and I will start with a general remark or with a general question. And you looked on the protection system for the DC grid from a perspective how you would design an AC protection system. So that means you have assumed circuit breakers at both ends of the line, and also then said, yeah, I would like to look how the protection can be designed using these circuit breakers, but you could have done it the other way around, coming from the converter and saying, yes, we have converters which might be capable of controlling the short circuit current, and then let's see what we can do on a converter side, because it's almost only software, and then design braking devices accordingly, which would have been a different setup. And I was wondering why you have chosen the first way. So that means the way you have actually chosen in your work.
Yes, that's a very good question, and I completely agree that there are many ways to design such an HVDC grid protection. For example, using the fault blocking converters and then smaller switches, which might result in reduced cost. Now, the reason why I looked into what I presented today is because the half-bridge MMC, which is non-fault blocking, is the dominant technology installed in the field, which is why I start from there. And the second reason also because the project had a bit of an emphasis on the full-scale testing of the DC circuit breakers. So now these devices are actually tested full-scale and proven in full-scale tests. But I completely agree that there are different methods to protection HVDC grids, and yeah, it's not like one is better than the other, in my opinion.
Okay, and what would you say if you look into the future, maybe 10, 15 years from now? Would things look different then, or?
I hope that things look different in the future. I mean, we have the DCCBs as full-scale prototypes proven, so I think the next step is to install them in the project somewhere, and I hope that happens not in 10 years, but hopefully earlier. So in 10, 15 years, I believe it's going to look different. And we see the first multi-terminal systems appearing in Scotland with the Scottish Caithness Marine, and we also see the first multi-vendor systems appearing with the with Equinor's parallel offshore links, Siemens and ABB.
Okay, thanks. And the second one regarding the general approaches, at the beginning you said that the double-ended protection is much better suited for having this, fulfilling the selectivity requirements on the grid protection. And then you considered single-ended protection in your thesis only. You commented on that during your presentation, when I said it depends on the length of the cable or length of the lines in particular. What would you say from which line length on you would then say it's mandatory to have this double-ended protection system?
So yes, so here I had a focus on single-ended fault detection, and that's really nice for shorter lines because you get a sharp signal. The line is not distorting the traveling wave so much, which is exactly as you say, more suited for shorter lines. Now, it's hard to say an exact number in kilometers for a line length where you have to switch over to double-ended, because it depends on the specific project, the specific cable, the power flows, and many different things. I think what we've seen here, the longest cable that we investigated was 296 kilometers, the extension to Shetland. And my feeling is that if you go beyond that, I think it starts to make sense to look into double-ended protection.
Okay, good. Then I have a comment or question regarding the setup of the IEDs, and in combination with the merging units. You touched that only a bit in your presentation, but in your thesis you explained it to a little bit more detailed extent, that here one approach is then to combine the merging unit and the IED into one device in order to have this kind of more efficient device. And my question is, if you now have this communication between the merging unit and the IED, which is standardized in the 61850, without going through this kind of bus, do you need to have special provisions, or do you need to inside the IED plus merging unit, or do you have to submit then the signals to a bus which is then available to other IEDs, or can it be considered as one, so to speak, integrated device for comprising both merging unit and the IED functionality?
Yeah. So there are two things I want to comment. The first thing is that IEC 61850-9-2, which is the standard for AC substation communication, and then the corresponding application note, as it is used today in AC, is going to be too slow for such a setup as shown here, because the publishing times for the measurement values are, now I forgot, but several hundred microseconds, and same for protection samples, trip signals. We get timings of, again, several hundred microseconds, which is too slow for this kind of fully selective HVDC with protection with DC circuit breakers. But I believe there's a need to combine the IED with the merging units, also with regard, obviously with regard to multi-vendor substations. So in a multi-vendor substation, I don't think it makes sense to keep the local measurements for, say, one line completely closed, but they have to be shared among different vendors such that you know what's going on in control, you know if a neighboring link, for example, has opened a DCCB, and so on and so forth. And I believe it's been done in the AEC world that the IED and the merging units are combined. So people talk about an intelligent IED. I'm not sure what this means because then it's intelligent electronic device. But I believe these approaches exist, and I believe it's necessary for HVDC grid protection. A last thing I want to say is, of course, there needs to be a certain level of standardization, but adapting the complete IEC 61850-9-2, which is a really complex setup to HVDC multi-vendor. You might argue that maybe that's not the first priority, but you could make your life a bit more simple during the initial multi-vendor projects, and you can maybe live with a bit more simple protocol in the beginning, just to get the. I don't think IEC 61850 is the showstopper for a multi-vendor HVDC setup, so to say.
But you would say it must be further developed.
It must be further developed, but these kind of communication protocols, in my opinion, should not be the first priority.
Okay, good. So then you mentioned, or you also explained it during your presentation, the detection margins for DC protection, which have been chosen to 50%. And it also was shown on slide number 16 on your presentation. And I was wondering why you have set it to 50%. Was it just by chance? Or, I mean, you could of course have set it to 60 or 40% or something different. I mean, it's more than AC, that's clear, but why 50%? Yeah.
Why 50%? It's an initial best guess. I'm currently running studies on what happens if you change these 50%, maybe you go back to 30, maybe you increase it to 70. But it's clear it has to be larger than in AC because here we're looking into transients for fault detection, which are much more impacted by all kinds of parameters as compared to a phasor-based detection that you use in AC. Therefore, it has to be larger. But I mean, a factor of 2 feels very large. So that's the initial guess. That's all I can say.
Okay. So you would say then, if it comes to more optimized consideration or optimization, could be even reduced then to a low value, or would you recommend to stay with this then for practical applications or real-world applications?
Right now I don't feel it should be reduced, and again it's just a number for the initial study. I'm not sure this is the value it should be later on as well. It's a value, an initial guess I used for to have an input for my optimization tool. I don't think it should be reduced. We have seen here how, for example, the surge arrestor curve can depending with different on what fault detection you use, you already lose 30% of the margin, and if the margin is smaller, then I mean it's immediately gone. So I would go for as high margins as you can without making it overly expensive. Ultimately.
Mm-hmm. Okay, thanks. Then you highlighted this problem with the margins also, or explained it in connection with a case where multi-vendor system, there was a lack of information, or information have not been shared among the vendors. And I was asking myself, is it really, was it really the case, or is it more, so to speak, an arbitrary case? And because I would say during your presentation, you said it's about PI, but I would say the value of the line reactance, I mean, it shouldn't be covered by PI, for example. So, and I would expect then if there is a multi-vendor system that at least the values of the line reactances will be shared.
Yeah, I expect the same. And I hope the same is the case. I mean, I'm just a PhD student in the university, so I don't know how these projects happen in the field and what you can talk about and what not. But here I assumed the most relevant aspects that are important for HVDC protection, and then I just took all of them and I went through what happens if you don't know those. And I mean, it makes the outcome is a bit of a grading here. So I mean, we have those where it's absolutely necessary to share this information, and these are also line inductor and threshold, and these are also the two that are actually most important for the HVDC protection design. And then the others, I don't see a failure, and I mean they're not the key input parameters to the HVDC protection, but still you have to keep them in mind.
Okay, so. Then okay, thanks. I would like to come to the holistic method for the optimal design you proposed in your thesis. And you said you see that the holistic method is more error prone due to automation of the protection setting process, which is quite reasonable. But I would say in principle, each and every setting procedure could be automated in a certain way. So means this is probably not the major reason for having it more error prone, or what would you say?
I'm not sure I fully understand your question, but HVDC protection has to be tested for each and every fault case, not once but several times to really be sure it's working. The reason why we test several times is, for example, also to take into account the sampling effects of several systems. A side effect of this setup is that during design, I already check all the test cases. So I have integrated the design and the testing, and that means when I have the output, I don't have to test again and then maybe manually go back to the beginning. I'm not sure that answers your question, but maybe.
Yeah, I know. Yes and no. I was wondering about the comment that the automation of the entire process as such is something which makes things better in your particular application, and because I would have thought that if you take any kind of design process, or you can automate it and you can have some sort of variation calculation of or parameter variations or something like this. And what is the special thing on your automation approach? That is probably the question.
I guess the first special thing is that I'm not aware of anybody else who has published on that topic. Despite a lot of research going on fault detection and protection design over the last years, to my knowledge, this is the first time somebody's doing that in HVDC. Now, optimization and automated settings is the usual approach in AC systems. So from that perspective, it's not a new idea, but it's the first time, at least to my knowledge, that this is being applied to HVDC, and it's in the public domain, so to say.
Okay, good. So, and during the optimization, I would say there could be local minima with the optimization approach. And how close can you come to the global optimum, or is it needed to reach the global optimum?
That's a very good question. So the background here is that this is a very complex problem, and with a very non-smooth solution space. So I'm going to talk a bit more about that. So because we have these discrete actions happening, so DTCB opening or not opening, or converter blocking or not blocking, this is a very discrete behavior, and that makes that the solution space is very non-smooth. So traditionally in an optimization, you expect maybe something like this. and then the optimization starts somewhere, and then you slowly move into a minimum. And here, this is the global minimum. And then here we have a local minimum also. But it's not super straightforward to have the solution space for this problem here. And it could, for example, be that, I mean, we get a curve that goes up like this, and then it comes back, and so on. And also we have a parameter space here with 10 input variables. So it's, yeah. So, I mean, but to answer your question, it's not strictly required to reach the global minimum. It's nice to have, but as long as you find a minimum and it fulfills all your constraints and you're happy with the solution from economic viewpoint, that's good enough. And also, with such a complex, non-smooth solution space, it's hard to guarantee that you mathematically that you found the global minimum. So with these heuristic, for example, genetic approach that I have here, they work very well for these kinds of problems, and there's a high likelihood that you find a minimum as compared to classic methods. But they can't give you a mathematical guarantee that you found global minimum. But I don't think it's strictly required.
No, it just needs to work at the end. Huh? That's the most important thing. Okay. Then the one of the part of the study was this EMT simulation. I believe you mentioned that in the presentation as well. And I guess that you have then had this detailed converter control inside the EMT simulation. And I was asking myself whether a parameter change in the control system would affect the result of your optimization, or whether you have studied it. Maybe you can comment on it a bit.
I have not studied that, but I believe it will have an impact, maybe not in the first few microseconds or tens of microseconds, but after that it's going to have an impact. And that's also why I say you have to study control and protection at the same time.
Yeah, okay. And how dependent is the result on the actual operating stage of the entire DC grid?
I believe you have to cover all operating points, different power flows, different AC site behavior also. Now, this is the first study, so I haven't covered those, but ultimately you have to cover all the operating points, yes.
So that means if before a real world application, then you should study extreme grid operating stages, for example, and then find a solution which covers all these stages.
Yeah, yes. And I mean, you have to test your protection also for all these kinds of scenarios anyway.
Okay, I see. Good. So then I would like to come to the open source protection ID. And first of all, I would like to mention that I really appreciate this idea and the approach of an open source ID for HVDC control. And I could imagine that this could also become a role model for the AC world, maybe, maybe not. But but here you said on your thesis, presented the speed of the algorithms you implemented in the protection device, and you also compared it to other devices. And if you look inside, or if you would compare your IAD with the protection algorithm with, so to speak, commercial ones, would you say that there are more algorithms inside in order to prevent the device for malfunctioning, or any kind of additional supervision instances in the device which would slow down the algorithms which have not been implemented in your laboratory setup?
That's probably the case. So I can't comment on anything about the Mitsubishi industrial prototype because obviously I'm not involved in building that. But if you compare an industrial grade IED to this open source prototype, then obviously I don't have dual redundancy here. I don't have to take care of EMI that much. And it's a bit a simplified system. So That could be one explanation. And I also want to mention, even though there's a slight time difference between the fault detection times, ultimately from a system perspective, we have seen that both work and both fulfill the timing requirements. And timing is not the only thing. I mean, ultimately, you have the important question is that the protection system as a whole fulfills the margins with these timings that are possible here.
Okay, so and what would you say what needs to be done in order to get this approach into a commercial available approach?
So I mean, the Mitsubishi IED, I believe, is a commercial device. For my IED here, I don't intend to make it a commercial product, but anybody who wants to use it can have.
But I mean, if you now say yes, we would follow the open source idea and then really take or put these devices into practice, and then of course there probably need to be further development in, I don't know, whatever, security or algorithms accuracy, or what would you say? What is needed before you can use it in the real world or in the field?
Sorry, are you talking about this prototype, or are you talking about the open source control and protection?
No, in general, I mean, this is a prototype, and now if I look on this from a general perspective, then of course you cannot use that into the, or you cannot put it into the field right now, I would say. So my question is, what would you say, what is needed in order to get there within the next years?
So I don't believe that there's a market for say I would do a startup on HVDC IEDs, if I understand your question. I don't believe there would be a future for that startup, because the substation is a complex story, and I mean, these kind of functions have to be integrated with the converter hardware, the measurements, and so on. So yeah, so I don't see how it makes sense to commercialize this idea as a single thing in a startup, for example.
Okay, so but if you now look a little bit broader on this, on the open source control and protection system in general for HVDC, then you mentioned that in your presentation already. There is maybe a little bit of work to be done in the interface between the open part of the control and the closed part of the control. And how would you say, can you approach this? How can this interface look like?
Okay, I'm slowly getting that.
Yes, this one, number 45. Yeah.
So this is an open research question. The potential of this open source external control is that you can investigate, and as a result, you have the tools to solve unwanted interaction in a multi-vendor context. So what it needs is a decision, or maybe several options on where to do this cut. So ideally, the control would be structured in a way that you only have things inside that don't have an impact on the external behavior. But that's going to be tricky, because we've seen publications, for example, how the sampling and the delay in the control system has an impact on the high frequency behavior of the converter. So that's something to keep in mind. To me, an idea would be to separate into current control and above here, and then you give the voltage reference there, just as a working hypothesis to start with, because I believe that's also how you structure and layer control systems with different portions in setup. But again, this is an open and ongoing research question. And then if you do that kind of thing, I mean, the behavior and the control specifications of that have to match whatever is inside. So you can't make the outer control faster, for example, than anything that is in the inner control. And then the second thing also is you have to coordinate with protection, because the MMC internal protection, for example, on overcurrents in the arms, is going to block the converter, and then from the upper layer, if you don't know that or you don't realize that, then it's going to saturate, and so it's nice to know these kind of things. And you can't avoid it. I mean, if the arm current is too high, the converter is going to block. I don't believe anybody in the open layers, in the upper layers, would have a say in that.
Okay. Yeah. Okay. Thanks. In the investigations for the IED testing, etc., you considered a star arrangement of the grid, and but maybe, as you also already mentioned in the presentation at the beginning, the star arrangement of DC grids will evolve to mesh grids, and also maybe some in the future we will have onshore DC grids which are meshed. And how would you say can your approach be applied to mesh grids as well, or do one need to add something or change something in order to have it ready for mesh grids?
So the open source, the proposal for an open source upper layer could easily be extended, taking into account the DC grid controllers as well. That would then be in the upper layer and openly available. And then there are questions associated about, okay, I mean, the DC grid is embedded into an AC grid. And if it's a large grid, you potentially have several TSOs who have different interests on how the power flow should be. So there needs to be a coordination there as well.
Okay, good. Yeah, thanks. So that's all from my side. So I believe really there are significant contributions in the thesis, and it was really a true pleasure to read it. Congratulations. So, and then I'd like to hand back to the chairman. Thanks.
Thank you very much, Dirk. Interesting questions. I think it's time to have a small leg stretcher. If you wonder what happened here with the Viking party, as Ilka closed the window, it's snowing outside here now, so we do have a Viking party. I suggest that we have a 5-minute leg stretcher before we go to the grading committee and their questions. So 5 minutes. So time for the questions from the grading committee. And I will start by geographical distance, and that means that I will first ask Professor Soledad Immaculada Bernal Pérez from Catalunya.
From Valencia.
From Valencia. Sorry.
Yes.
I'm mixing it up. Sorry.
That's further away. Yeah.
Valencia it is. Welcome, please.
Okay, so the first thing that I want to say is congratulations for your presentation and your work. I can see findings and results, but I can also peer at all the hard work that is behind. You have made an approach of a very, very complex issue. As you have mentioned in your document, that it sometimes looks like a chicken and egg problem because you don't know how to start. There is no grid code, so you have to make some assumptions, and after that, yes, suggest something for the grid code. I think there is a problem that have several iterations, and I think that your work can be considered as one of these valuable iterations. So congratulations for that. I had questions, but most of them have been answered to your opponent. But I have just out of curiosity. There are a lot of work done in this thesis. You have optimization, simulation, protection algorithms, and field data. Also, you have worked with field data. And I want to know how much were you involved in the prototype design and implementation?
Yeah, thank you for this question. So the prototype design for the intelligent electronic device, that's something that was mainly done here in KTH by me. So The main board is something that everybody in the group is using, so there's some overlap, so you can help each other. But the design of the connector cards to connect to the RTDS, putting everything in the box, specifying the inputs, outputs, and so on, that was me. And then there was a bit of help from a consultant to get the software infrastructure.
Okay.
But the coding of the algorithms and so on, and the hardware, that's my work. It takes a long time.
Yeah. And you have presented your prototype for research, but also for educational purposes, as in your paper, I think is number 2. Okay. I would like to know, from your point of view, which advantages you have when you use this device in with training instead of another kinds of simulators or SCADA or Simulink or whatever.
So the advantage of having a physical device for these kind of studies is that you have something to show. You can bring it here in the room. So when I'm teaching with that device, it's in this room. I can put it here. The students can see it. They can move the sliders. They see a feedback. An LED turns on, and that's cool. That's nice, and that's why there's an increased interest. Now I can't compare to teaching without such a prototype for the HVDC protection topic, because I've never done it. So if from a very scientific viewpoint, comparing teaching HVDC protection with and without IED, I can't compare it. But my feeling is that the students appreciate it, they find it interesting, they come back and then they say, but can't we do a project? And there have been actually 2 master theses resulting from the teaching with the IED. So I think the students like having something where they can move sliders and do a bit of a lab testing.
Okay, so thank you for your answers. I have finished with them. Thank you.
Thank you very much for your comments and your curiosity and your questions also. With this, before I proceed in the grading committee, I would just like to remember the attendance, that you can put questions in the Q&A. I have some questions in the Q&A, and you can also raise your hand electronically, and I can let you put your question orally if you want to, and that would be really nice if someone would like to put a question orally. So with that words, I would like to go to Professor Oriol Gomis Bellmunt from Catalunya.
Yes, thank you. Yes, this time from Catalonia. Thank you for the presentation. I also wanted to sum myself to the congratulations from my previous colleagues. I think it is very interesting work, and you have presented it clearly, both in the papers and the thesis text and in your presentation. I also agree with my colleagues that it is a very complex topic, combining many important challenges, and there is a large research community addressing these challenges in several projects. And I think your work is providing interesting novel ideas there. Also, I think it is very important that you are combining work in your lab with combining RTDS and measurements from the field, and working with these IEDs all together. So, we know it's demanding work, but the results are interesting. And also, I wanted to mention as well the added value of your work on educational tasks, and also the orientation to open solutions and the analysis of developing open solutions, which of course it is something very important to develop the technology and make sure it can work, also combining multiple vendors, multiple parties, and probably for people in the world of the research, it is important to have these tools and to allow more people to provide contributions to the field. Okay, so in this sense, I think all this is very, very interesting. I have some questions. Well, adding perhaps trying to add something to what it was mentioned by my colleagues before, which were already asking very important questions on the topic. Perhaps the first one related to the second chapter of the thesis and perhaps the introduction of your topic. You have explained very well the difference between the single-ended and these double-ended protections, and also the implications in designing the system and the inductances you may need. And then also later you focused on the single-ended protection and analyzed also like the sizing of the inductance for different applications, and also using later your optimization and so on. I wanted to ask you if you were asked after finishing your thesis, because normally the opinions can change after doing such a large amount of work. After finishing your thesis, if you were asked in general about a new HVDC project, if you recommend single-ended or double-ended protections, what would you recommend to the developers of this project?
I would say that depends on the project. But I would never discard double-ended just because a line is too short. I think it's a relevant. I mean, you need a communication structure anyway, so you can as well use this information, maybe even for backup purposes. I don't think there needs to be. It's hard to give a general recommendation. It depends on the project. For example, for overhead lines, I would always do double-ended. And long lines always double-ended.
Okay, and do you think, also another perhaps a general question, do you think the methodologies and the algorithms you have developed for the analysis and optimization of the system could be perhaps expanded, considering also the double-ended protections, and perhaps also the possibility of changing the protection zones you consider in the system, in order to perhaps find the best solution? I mean, because at some point there can be a trade-off between the size of the inductance and the use of or not of double-ended protections. So perhaps optimization tools like the one you developed could help here.
Yeah, so I agree there's a trade-off. I mean, sizing of the inductor, complications involved by making it very large. At some point, it might make more sense to go to double-ended. Now, the algorithms that I use here are for single-ended and work well in cable networks. So for double-ended, there has been a lot of research ongoing in differential current criteria. So given that this is the common approach, I would focus from there. I would not start with the DVDT as used in single-ended and try to expand it to double-ended.
Okay. Another question on the chapter 4. You have been analyzing uncertainty, which is a very, very important topic. And basically you were doing some assumptions on Bronc parameters, which could be considered, and then analyzing the impact of these Bronc assumptions, let's say, or this Bronc parameters assumption. My question was, how have you chosen these Bronc parameters? I mean, is it something important? I guess it is important how you choose, like the Bronc parameter, because of course the results will depend a lot on that. What criterion have you used to decide how Bronc the parameter is in the analysis?
Yeah, so the list of parameters I investigated are the criteria that have the most impact on the behavior of the HVDC protection system. So starting from thresholds and line inductors, and then some things that I observed in my work, also down to the software filtering. Now, the test cases that I show you here, that I showed here on the line inductor, and also the other test cases in the paper and in the thesis, are if you want to say it like that, I searched as long as until I found a case where the protection failed or didn't perform as I wanted. So you can argue that this is basically engineered for failure, but at the same time, the inputs I used or the parameters are not like completely out of anything you would consider normal. So it's still in the realm of possible things that can go wrong, assuming that knowledge about one of these parameters is lacking. But this is not a systematic study. It's based on what I learned over the years and my feeling of what should be important.
Okay, yeah, thank you. Then about the optimization, you are dealing with a quite massive optimization problem, and there you need to go for heuristic approaches, which is reasonable, I think, in this case. In your case, also you are considering two possible objective functions, like the total inductance you are using in the system, and also the energy. And sometimes in some studies, when we have to deal with systems where we are interested in optimizing perhaps different objective functions, you know, we have this multiple objective function approach. And one interesting figure, which I have not seen in the thesis, is you know, these Pareto fronts, where you can see how the trade-off is working between these two quantities we want to optimize. Like if we are increasing one, perhaps we are decreasing the other. And I wanted to ask you if you have made a study of this kind, you know, to put together the inductance and the energy and to see how the depending on what you were optimizing, how it was changing the result, or if it was possible to do some kind of multiple objective functions, or if you have some thoughts about how to combine the two objective functions.
Yes, yeah, I completely agree. That would be really nice to see. So just a trade-off between line inductor and maybe DTCB energy requirements. That would be very interesting to see the optimum in between. Now I have not done that yet. I have tested some mixed multi-objective functions, but not in a systematic way. But I think that would be very interesting to see.
Mm-hmm. Okay, and another comment related to this is that you have defined a limit for the inductances, like a minimum and maximum, to avoid the optimization giving some unrealistic values. And then it seems in some of the cases, I think there was one table, I think it's table 5.2 in the thesis, you were reaching the maximum, right? So the optimization was bringing the solution to the maximum inductance. Would it be interesting also to leave this, of course, assuming that you are not going to build this, but would it be interesting to let the optimization find out what it is the optimal value instead of constraining it between two values? And then once you obtain the optimal value, then you can decide not to go for it because it is outside your limits. But I think to let the optimization find it can give some valuable information.
Yeah. Yeah, I haven't thought about trying that.
Mm-hmm.
One reason why I restrict the upper limit is to save optimization time at some point, just to limit the possible inputs. But I haven't tried that. I haven't thought about that.
Mm-hmm. And another comment on the optimization. As I mentioned before, using heuristics, it is reasonable, I think. But sometimes, we have the doubt on which of the thousands of methods available related to heuristics, which one we should use, if it is the birds, the ants, the genetic algorithm, whatever. And sometimes we discussing with colleagues, it seems that if you are using random generation of different quantities and trying with them, at the end it is what these algorithms are doing in essence. My question was, do you think if you were like choosing the same number of solutions you have studied with the genetic algorithm, if you were choosing them randomly and comparing, would you obtain perhaps similar results? Or do you think this genetic approach, it is really giving a clear advantage?
So the genetic optimization since it is a heuristic optimization, gives a clear advantage compared to classic optimization. Because in the classic, I mean, it works well for a smooth solution space, and then you try to move along and end up in the minimum. And because this is a complex problem, the more classic optimization methods, they just like get stuck in a local minimum that's actually really not remotely close to the global minimum, and they run for a very long time. So actually, I spent a considerable amount of time trying the classic methods and configuring them in different ways so that they maybe work. But ultimately, yeah, it's a bit like you described. So then I had a chat with the colleagues from the power systems who do that a bit more often, and they suggested the genetic optimization. And since it's heuristic, it's an advantage for these kind of problems. But I can't comment on different heuristic methods and how they would compare.
Okay, yeah, thank you. And well, my last question related to the chapter 7, where you use the field validation. I was a bit surprised by the results you were showing. It is in figure 7.1 in the thesis. I do not know in what slide in the presentation. And perhaps, and also revising that in your paper, there was very little information on the field measurements. Yes, well, perhaps not this one. First comment about this is that it is very valuable to have field measurements, and of course, this kind of system, it is not something easy to test. So I appreciate a lot the field measurements. My surprise was mainly for the voltage. Here at time instant 1 second, you have a fault in the negative pole. And in the positive pole, I think we should expect to have a higher increase of the voltage. And yeah, in this figure, we can see that this voltage seems to stabilize in a value which is, I don't know, 400 and something. And normally we would expect a higher value of the voltage, you know, like the negative is moving to minus 300 to 0, then the positive normally should increase also similarly.
Yeah.
I just wanted to ask you about these results, if this is something, if I am missing something, or it is something which was, well, perhaps you could explain a bit more these results, or perhaps I don't know, I'm not understanding something.
Yeah, so I can't comment on any details of the actual system, obviously, because I don't know. I mean, this is a symmetric monopolar system. You expect a voltage increase on the positive pole. I mean, I would assume here maybe the surge arresters are a bit more tightly dimensioned. So if you take a 1.4 per unit surge arrestor, you end up with 450 kilovolts, which is a bit what we see here. Maybe that's the case, but I don't know.
Yeah, okay. Yeah, okay. That makes full sense. So here you are also, of course, the surge arrestors are limiting the voltage, and this is the reason for this voltage limitation. Okay, yeah, that's clear. Okay, thank you very much. Then this is everything from my side, and congratulations again for your work.
Thank you very much, Oriol. Then we move on a bit closer to Sweden, so we go to Professor Tim Green at Imperial College. The screen is yours.
Thank you. Thank you indeed. And thank you very much, Ilka. Congratulations on the work you've performed, and thank you particularly for what I thought was a very clear presentation. You covered a lot of ground in approximately an hour, and you kept the messages crystal clear. So congratulations on that as well. Yes, my esteemed colleagues have not left very much for me to question, but I'm going to try. And I think I might try and go a bit more general. So we're here discussing HVDC protection because, as you say, it's more complex and it's quite different to the way protection is done in traditional AC grids. And I wonder if we could sort of separate out why that is. It seems to me there might be three reasons. One is it's DC, so inductors behave differently. One is all of the nodes have an active controlled element, so the control scheme is relevant and more prominent perhaps. And the other is the issues of sort of protection of intellectual property and ownership of equipment. And could you sort of describe how you see those three things play? Which of those are the ones that most complicate the issue, and you know, what examples of technical features fall into those three categories?
We had three categories. That's the
Do you want me to repeat them?
HVDC, I can try. HVDC protection behaves different compared to AC. The second is the active controlled devices in all nodes, and the third one is the intellectual property question. And to me, the most complex and complicated is the intellectual property question, because we see that the individual, point-to-point links are installed. Single vendor point-to-point links are installed in the field. They work. Different pieces of equipment have been tested for several DCCBs full scale, but we see a bit of hesitance towards multi-vendor systems. And a key issue here is the intellectual property, the function specifications. Then we have to keep in mind this is still a very this is a developing field, so we have new solutions coming in. You don't want to specify and too strong and then stop potential future development for even better solutions. So that's where you have to find a trade-off. And then we see, like, if you, ultimately these things have to be installed in the field if we want to exploit the wind energy potential. And so, for example, last week NSOE published a report on this vicious circle of specifications. So as a vendor, you need specifications from the TSO, but the TSO doesn't know all the details about the equipment, so it's hard to specify. And then how do you write a tender? So it's complex. It's complex equipment. There's a lot of hardware and software interactions, and yeah, the main question to me, the main difficulty is the point 3 that you mentioned. But the reason why it is so tricky and why the intellectual property and the specifications are so complex is because of numbers 2 and number 1 that you mentioned. That's the impact of the software, control systems, and the very dynamic behavior in the protection.
Yeah, that was very clear. Thank you. Yeah, so you mentioned NSOE and system operators, and my thoughts were going in that direction also, that one of the things, in a traditional grid, we wouldn't be arguing about whether vendor B needs to know details from vendor A in order to design protection, because a system owner operator would be responsible for protection systems and would purchase equipment for it. And are we building in problems because we're putting too much on vendors, and then you're in a multi-vendor situation, which is difficult. If more of this was in the realm of a offshore transmission operator who had a relationship with vendors where they could disclose IP, would that unlock a lot of the problems, do you think?
I believe it would be very useful for more complex systems and multi-vendor systems to have somebody who takes on the role of a system integrator. Could be a TSO or could be someone else. But I don't believe that has to be the case for every single project. I mean, if you just want to build a point-to-point link or a single vendor multi-terminal system, then it's perfect. I believe it's, this is how you do today. It's working perfectly fine. And if you, as a TSO, you might have a good reason to do that in the standard and established approach. It's just in situations where it becomes more complex, I believe it could make sense to have, as you say, an integrator role somewhere.
You talked about this chicken and egg impasse where a system operator needs to know about what equipment can and can't do before it can write a specification, and a vendor needs to know the specification before it can design equipment. And it's there particularly in HVDC, as you've said. It strikes me that it's emerging in AC systems as well because of the huge changes in AC systems, the standing down of traditional generators and much higher fractions of wind farms and solar farms and indeed HVDC. What do you think the lessons are that we're going to learn from HVDC protection that we might take into AC protection when AC systems change?
Okay, to answer this question, maybe I can quickly say what I believe is the main difference, and that is that HVDC converters are very expensive, very specialized equipment, and because of that they come with all these functions from the internal protection to different operating modes and so on. And then I guess if you go down in voltage class, it becomes a bit less complex and less complicated. The lessons we can learn from HVDC for AC systems, I guess it's that a certain degree of openness is required. For example, last year I was in the last conference before Corona. We had presentations on AC protection relays and how they are impacted by converters in the vicinity. And depending on how these are programmed and how the different AC IEDs are programmed, I think the statement of the person presenting was, "I had no clue what is going on in this IED and what the software is doing." So it's really hard to configure it, and I guess that's a lesson that it's not a lesson that you can learn, but it's an overlap.
Yeah, thank you. That was a very general question and maybe a bit unfair, but thank you for the answer. I appreciate that. Maybe I should go back to things that are more core in the thesis. So I was looking at the section on the design optimization, which you've discussed already with my fellow panelists. But I was interested in this difference you see between blocking and not blocking converters. And you see that blocking converters end up with higher inductance requirements than converters that don't block. And can you help me understand why that's the case? What is it in the performance that leads one to have a higher inductance requirement?
So what happens in the DC side short circuit is that at some point this short circuit is drawing a current coming from the connected cables and then ultimately coming through the converter from the AC side. So ultimately there's a high current or a rising current flowing through the converter, and if this current goes above the capabilities of the semiconductors, the converter is going to block the cells and bypass them, which means in a half-bridge case it's not controllable anymore, and you can't support reactive power to the AC side.
Yeah, so maybe I just need to be careful we understand the same thing by blocking. So in the blocking case, you stop switching the transistors in the submodules.
Yes.
And in the non-blocking case, you allow them to continue to switch, but they are still no longer able to control the current. They don't have enough voltage available to control the current. But what happens? Do they just partially offset the current? They manage to reduce it a bit, but not control it?
I have not implemented any special control addressing the DC side currents or fault currents, but because they don't have to be bypassed through the high current, they can continue operation such that you can provide the service to the AC side.
Okay. I think this sort of connects with questions that Professor Westermann asked you earlier, because the other category of converter is one that has enough full bridge cells or some other circuit configuration that lets it control current. And the thinking is that if you control the currents, you would have less need for the inductance there and maybe lower energy requirements in the circuit breakers. So, and then in conversation with Professor Gomis Bellmunt, you discussed how double-ended protection would lead you to lower inductance values also. And that seems to be really quite a good way of sort of breaking the trade-off between inductor and value and energy rating of the circuit breaker. the combination of fault controlling converters and double-ended protection seems to quite strongly drive you to a better trade-off, I think. Is that your understanding also? Would you like to comment on that?
Yes, I agree. The two points. One I brought up earlier was that, again, I looked into half-bridge DCCB solutions because these are the equipments that are either dominant or tested full scale. And the second is by controlling the current and then voltage down in all the connected links. If you have a very large grid, then the power flow in the DC grid is out for a few hundred milliseconds until you can start it up again. And that's perfectly feasible if your AC grid can do that. But if not, and if it's a very large grid, then yeah, then you can't do that, basically.
Okay, yeah, indeed, and I know sort of co-authors on some of your papers have views on that as well. So that's the sort of the extreme version, is it collapse the whole when there's a DC fault, collapse the whole DC system, isolate, come back up, and as you quite correctly say, you have to be sure that your AC system can survive that momentary outage. But is there a sort of a less severe version of that where you use the fault controlling converter simply to reduce the fault currents and therefore not have to have as much inductance and does that in any way make it easier to detect the fault?
I believe so. It sounds very reasonable what you're saying. I have not looked into that. I mean, the advantage would then be that you need DCCPs with less energy requirements, which is less expensive. Maybe people are more likely to install those in the field as compared to a 20 megajoule, 20 kiloamp DCCB.
Okay. Yeah. I realize I've taken you a bit beyond what's strictly in your thesis, which is a bit naughty, but it seemed to me you were in a good position to answer those questions, and I was genuinely very interested in the answers. So thank you for responding to all of those questions, and again, congratulations on the work. Thank you.
Thank you very much, Tim. I'll try to remove the spotlight now. And then we move even further to ground zero. So we move to Gothenburg and Professor Massimo Bongiorno. I call you on the screen now. Welcome.
Yeah, I am. Thank you, Mats. Yeah, so many questions already, good questions. So I miss Italy. It was easier to be close, but far away. So Ilka, congratulations also from my side on your work. Definitely interesting, and I mean challenging also, because I mean there are not many of these installations in the world, so of course it is tricky. I have also very generic questions, except maybe one that is related to your work, as a lot of questions have been already asked. Maybe one thing that is also can be seen also as a small criticism on the thesis is that I missed what is the grand challenge here. What I'm saying is that there are very few multi-terminal HVDC, right? And when do you need a DC breaker? Or do all multi-terminal HVDC have a DC breaker?
So the multi-terminal HVDC grids in China do have DC breakers. You need them if you need a certain power flow in the HVDC grid, such that you can provide the required power on the AC side.
But what I mean is that, for example, I think also in your thesis you mentioned the Nanao, I think it's called, sorry for the pronunciation, 3-terminal HVDC in China. And there I think that there is a DC breaker. But I mean, my question is, do all multi-terminal HVDC need a DC breaker? When do they need a DC breaker?
Not all multi-terminal HVDC systems need a DC breaker. you need a DC breaker if from the AC system, you need a continuous power flow. You have to, in case of a fault, you disconnect a certain part, the rest continues operation. You can also think of setups where you can, for example, use a DC breaker to bypass a certain piece of equipment. And then in case of a fault, you can reverse, send the power somewhere else.
So probably it's also when basically the AC protection will fail in protecting the link.
Yes, exactly. So I mean, or if you need StatCom somewhere in a point-to-point link, if you need StatCom, for example, southern Sweden, connected with a point-to-point link, then you can connect on disconnect on the DC side.
Okay. And then, I mean, if we move from the multi-terminal now to the probably futuristic DC grid, I mean, you have been investigating this benchmark model from the SIGRE with the diagonal line also. And then you have seen the performance of the system, detection time, etc. But I mean, if you have this type of configuration, shouldn't you have also other components in the DC grid that can have an impact on your system?
So you're asking about other components in DC grid that have an impact on the system.
On your on the response time, or on anyway on the performance of your DC breaker.
So the performance of a DC breaker depends on the technology used, and basically the complete surrounding grid. That means the cables, length of the cables, the converter systems, what the control systems do.
Yeah, my question basically is if you can bring up the SIGRE test benchmark model. Yeah, thank you. I mean, here you have 4 converters and 5 cables, right?
Yes.
So can you really control the power flow in this network?
Well, it depends on which cables are connected and are not connected.
Yeah, I mean, basically my question, I guess that when you start to mesh, it could be that at some point you will need also DC-DC converters to control the power flow.
Okay.
Different kind of DC converter. I'm not saying that has to be one or the other. And I guess that this might have an impact on your studies.
Yeah, I guess it does not have an impact on the initial incoming traveling wave. So the fault detection would be, the actual fault detection I expect would be very similar. That is mainly impacted by the length of the cable. So how much is the away from a remote fault dampened, and it's impacted by the line inductor used for the DCCB. So I guess for the IED operating times, I don't expect that the DC converter somewhere would make a big difference, but it might make a difference on if you look into the DCCB design, which is a bit out of the scope of what I did, depending on what the control is doing and how much energy is stored, that might have an impact. So, and then it's less about the IED operating time, but maybe more about the optimization. Yeah, but that would have an impact, I believe.
No. Okay, if we say on this figure here, something that I'm not really an expert on, but I mean I've heard from a lot of different sources. Let's say that you have your protection on bus 1 and bus 4, and then you have looked on the use of single action or dual action or double action. And then you were discussing with Professor Westermann about the length that you have considered on where you might need the double action instead. And then you mentioned 209 kilometers is what you have tested. And then let me say, above this, you might need it. What will be in this case the impact of the latency in the communication? Have you considered it in your models?
So this number I mentioned is simply how long the longest cable is that we tested in the real world.
Yeah, I know. I mean, it can be 300. It doesn't matter the number.
Depends on many things.
Yeah.
The impact of the latency of the communication. If you use a double-ended fault detection, it can have an impact. So, for example, if you have a, maybe I switched to whiteboard. So, if you have a cable, and here you have the local ID. Is this showing?
No, I think it doesn't.
I don't see it. Sorry.
I think you have to use the share because, or else we have to rearrange this.
Okay. So in a cable with a single-ended fault detection, if you,
Now I see it.
Okay, now you see. If you have a closed fault, that's fast to detect. It's a strong signal. There's not much of a latency. Now, if you were to use a double-ended fault detection for this kind of fault, then the traveling wave has to go here. That comes with, say, 200 kilometers per millisecond. Say that takes a millisecond. Then you have an IED here that has to detect a forward fault. That takes maybe another half a millisecond. And then you have to send a communication signal back. Okay, that's not really working. Another millisecond. So we're at like 2.5 milliseconds extra as compared to only detecting single-ended. But if you have a cable with the remote fault here, then actually it takes a millisecond for the traveling wave to arrive here. So now we're having a double-ended setup. So we have an IED here, and that detects this closed fault almost immediately, and it starts sending the communication about this in the same direction. And because it's I mean, optic fiber also is around like say 200 kilometers per millisecond. So you will only get a delta t in a rough assumption that is 0.5 milliseconds. So that's why double-ended is beneficial for remote faults seen from this end, and single-ended is beneficial for close faults.
Okay. One last question related to the open source control. I think that in general, of course, it's a very interesting and good idea. Maybe it's not that easy to realize in practice, as what you call open source external control and closed internal control, they interact with each other. But that is my comment. But I got interested on one thing here. If you look on page 52 of your thesis, for the technical challenges, you write, on a technical level, several questions need to be answered. First, an open question is whether and under which condition the statement holds that the circulating current control and lower level controls do not impact the AC side admittance. And then you refer to two papers. One of these, I think, is the one from Kalle, where they say that they basically state the opposite. So the first question is, why are you talking about the AC side input admittance since you're working on the DC side?
And this is a proposal not only targeted on the DC side, it's also targeted on the AC side. So as for example here, I mean, you can have the interactions through the AC side as well.
Yeah, but I mean, before we were discussing about the DC side, so that is why
Yeah.
I am bringing the question. I mean, what about the DC side?
So depending on how you design the control, you will also have an impact on the DC side.
But have you, I mean, have you read? I mean, of course, I'm sure you have not had even the time to look at the input admittances and these kind of things. But have you looked for references if the input admittance from the DC side is impacted by the what you call internal control? Or?
So when I wrote this, I did not look at that. I believe there are publications out there you've published in this area where you can look this up.
Okay, fair enough. Okay, then that's it from my side. Thank you very much, Ilka.
Thank you very much, Massimo. And that means that I'm almost approaching a short circuit, because I will call Docent Nathaniel Taylor, and I think he is just below us in the same building, almost at least. So let's hear what you have to say about short circuits, very close to the respondent.
Ah, okay. Do you hear me and see me okay? Yep. Thank you. Thank you, Ilka. That was, I can't resist saying, as well as many others have said, that was very good and clear, well put across, and it's an interesting set of topics. And yes, of course, there's plenty I could have asked that's redundant now. That's good. And I would like to focus on just a very small amount of it here, mainly about your testing. I think one of the points there is that what's missed is important. That is, what cases one shouldn't operate for, a very big part of the testing. And that seems to have been the case with yours too, that you had a lot of faults in different places in the system. And you even looked at the questions of the margin that's needed, the limitations of the sensing and possible disturbance of signals. For AC testing, there's an awful lot more that's done, but I can imagine, tying back to what Professor Green asked also, one of the advantages that you get actually with working very quickly, very short times, and in the time domain, is that you miss out a lot of the other things that can come, the spurious phenomena that you can get if you're looking at fundamental frequency AC, as is common with AC protection. In those cases, in some sorts of systems, there's a lot that can go on that could, in some special case that one didn't think of, turn out to be a problem for the security, a false operation. But I think in your case, you probably are quite safe with that you're working with well-defined, very quick signals, and they have to be quite strong signals too. So I can understand that this testing is probably rather thorough and that you've taken into account some margins, I mean, for the test system that you've looked at least. So my question here would be, suppose that against what you said, you actually have started a company that is giving these giving a relay based on this prototype for use in a real system. And you get a phone call saying it's operated when it shouldn't have done. What would be the first thing that would come into your mind at that point, as what direction you'd have to start looking? Yes, obviously you'd start looking at fault recordings and so on, but as the first guess about what is the weakness of your testing, what would you say?
So I would never do a startup on this kind of equipment, just to mention that. But looking into, you get a spurious trip, the security was not right. Where would I start looking after having had a look at the fault recordings? I guess I would have a chat with other people who are involved in substation and in the design of the overall system. We can have a look at general phenomena that might have had an impact on the power flow, maybe weather conditions. I'm not sure how to address your question.
No, okay, sorry. The question was more about your first thought. I mean, if you had to think now of a weakness in what was tested, what would your first guess be about what really should be increased, or what other phenomena should be thought of? What things could happen in a real system that could cause problems for the security of your methods or of your device? Is there any particular one thing or first?
I mean, in the testing, I did not cover all the range of possible things that can go wrong. For example, for the optimization, I did not vary the fault resistance. For example, here I took a relatively bad value, so a worst case, but I did not vary it systematically in this first study. So that's something to take in mind, to keep in mind.
Okay, yes.
Sorry. Or explain what you mean a bit more detail?
Yes, I'm sorry, I made it confusing, but the basic question was, what would be your first guess as the most important thing that you're not really testing for when you do your automated tests? But I was trying to dress it up to be more exciting in terms of you've got a problem and what's the first thing that comes into your head. But I think you've answered it with that sufficiently. So I really can't think which I would consider more likely to be a problem, either that you should have modeled more different kinds of events, or that you should think more about the sensors and what problems they might be introducing. But that's fine. The only other thing I'd like to push a little bit further on is the purpose of being open source. Can you elaborate a bit on that more? I don't disagree. I think this is something with potential usefulness, although whether it will happen at all soon is a different matter. But what are the actual advantages of this, apart from being a buzzword?
The advantage of an open source higher level control in an actual HVDC substation is that it's going to be easier to look into causes for potential interactions, and then also to solve them. And I mean, open source in industry is not like just a funny idea, but people have business models on that. They use this as a tool to interact. You limit potential for vendor lock-in, and you have an option also as a customer to look a bit more into what is going on, understand unwanted interactions and solve it. And the second thing is, now if we think in the future, if you install an HVDC link in the field, it has to last several decades. And just because you program and specify a control and protection system today doesn't mean it has to be like that for the complete lifetime. Maybe there, or potentially, probably, there are many more converters appearing in the grid. Everything is going to be power electronics dominated, control dominated. So at some point, I expect you have to adapt certain parts of the control. And in a multi-vendor setup, an open approach, I believe, could make this easier.
Okay, so you've mentioned being able to see what's happening, one understands better what's in the box if one has the patience to read through potentially quite a lot of code. But that's good. And perhaps to be able to do things later with it, change it oneself, although doing anything like that, of course, might give some risk of how much support you're going to get. Yes, I would just add, though, that another potentially useful part of this is if you ended up with lots of vendors actually using basically the same thing, not having to repeat lots of the basics, but they use one very well tried and tested piece of code and just make their own small changes, well declared. I mean, that's what we see with Microsoft using Linux code quite a lot in its Azure services and all kinds of things like this, that when everybody is able to be modifying it, they can all start sharing the same base. And then you might get something that irons out some of the bugs that otherwise would have been different little bugs in everyone's own private software. So I think this is also a potentially useful side of it. But as you've already said, we can't be sure what's going to happen with the manufacturers. Or I could see either extreme, really, that people just keep their proprietary code and nobody's interested in pushing them to do otherwise. or that it actually becomes fully open and that people are sharing much the same code base, and that this is sort of commoditized. It's not anymore a big part of the value of what's being given with an HVDC scheme. Perhaps the focus would be more on the hardware then. Final thought, I wonder if you could give a very brief opinion of the situation with the industry now. If you were to want to protect a multi-terminal system, do you think there would have been a problem with getting industrial providers of the relay hardware? You mentioned the Mitsubishi hardware. If somebody wanted a system to be built in the next 5 years, what do you think would have been the case? That new hardware would have had to be produced by the manufacturers to a specification, or that there would have been a severe problem with actually managing to get this up and running?
Now, I obviously can't talk for any manufacturer, but given that, for example, DCCBs are tested full scale from several vendors, and the respective fault detection IEDs or also DCCB control systems have been tested in independent labs in real-time simulation, not only in this project, also in other projects. Well, I don't believe there's need for a huge hardware development for IEDs. And then also, I mean, the main behavior is not defined by the IED hardware, but by software inside.
Mm-hmm. No, I felt this too, that it's nice to have the hardware in the project and that you've done. And it's interesting to consider the option of having more open source even for these sorts of things like the protection algorithms. But I was imagining that there are solutions that could be quite quickly produced anyway by vendors, since they've been produced along with the relays, or at least a lot of the concepts will have been tested along with the relays. Yeah. But, okay, yes, I don't have any more significant questions there, but thank you again.
Thank you very much, Nathaniel. And that was the last question from the grading committee. However, we have a stand-in member of the grading committee, Dr. Yangping Wang from Hitachi Power Grids, and he would like to come in and put some questions also. So please, Yangping, the screen is yours.
Yes, thank you, Ilka, for your nice work, and also combined with both theoretical and practical practice in the thesis. I would like just to give a couple of questions in short. First is that the DC grid from the practical or industrial application. Since we have discussed this for last 10 or 15 years, so what's your view on the real application on DC grid, so-called implementation? As we mentioned before, up to now we have only saw the multi-terminal station in China, but in Europe continent we didn't saw any DC grid, and also in US we have not seen any DC grid project. So can you give some comments in this area for the future potential project?
Yes, I mean, we see HVDC grids being put into operation in China, but not in Europe, though the individual parts have been tested and shown to work, and we also see that it's working in China. So why not build it here? And it has, to me, it has to do with, I mean, with organizing all this setup where you have multiple vendors, you have to specify, you have to do a tender. This is not super straightforward. That's one aspect. The second aspect is that at least I mean, maybe the need to build new power lines in Europe is just not as much as a driver as it is in China, but I hope it is going to change in the future with more offshore offshore wind being implemented. Yes, I hope I addressed your question with that.
Partially.
Which part is missing?
Actually, I wanted to know is there some real demanding in the practical project to formulate that kind of a DC grid?
Yeah. I mean, I've never worked in an actual HVDC project. Obviously, I mean, I'm a PhD student in the university, but my suspicion is that the challenge is to specify everything correctly, have the right functional specifications, have an option to iterate, such that you can start building this. And then maybe a second thing is also you would need a project where you can start trying this equipment, but you're not maybe 100% relying on that. So if such a project occurs, that's a very nice testing case.
Thank you for the.
Yeah. If everyone has a bit more confidence, then hopefully taking off.
The second question is that from your study, your system is a cable-based system. Because for cable, the fault always is a permanent fault. Have you considered the overhead line, or in the future could be the mixed line? That means overhead line with the cable or some kind of a mixtured combination, because it is practical that you have sea, you have the shore, so you may have high voltage station far away. So have you considered those things in the future?
I have not considered it in this project because it was a project about meshed offshore grids, so obviously cabled, but I believe it makes sense to look into overhead lines as well. So now the behavior is a bit different. It's much more dynamic. As we've discussed before, can make sense to look into double-ended fault detection there. You might consider DCCBs with reclosing. Yeah, but then on the other hand, if we look at Europe, overhead lines are very unpopular. So what we see is that even on the continent, the new systems are for large portions cabled again.
Okay, another thing is regarding the latency. Is a kind of a clarification. Say that for the previous discussion that you're talking with Massimo from Chalmers, the latency clarification is that the communication channel normally they have 3.3 times latency time. So for example, if you have a fault in the remote end, 300 kilometers, so-called the overhead line with the fault there, it will took another 3.3 milliseconds to the local end by the fiber communication, because the fiber communication is not the light speed directly. It has some reflection in the fiber optical links. So they are a little bit delay compared with the light speed. So it's 3.3 times according to the industrial experience. So just clarify this. Yeah, but anyway, I think I would like thank you for your answer, and I hope you, thank you for your hard work in the area. Congratulations to you and also all the people participating in this effort. Yes.
Thank you very much, Jean-Ping, for your questions. That ends the extended grading committee, and I do have some questions also from the attendants, and I will try to phrase them. I might, if any one of you would like to put it orally, I can unmute you and you can do that. But I start with a question from Niklas Svensson. How is the objective minimum sum of inductance combined with the requirement for a reliable, stable system also after future expansions? Must future expansions be known? Is it beneficial in this aspect if future expansions are known, or does it not matter?
No, it's thank you, Niklas. That's a good question. I know we've discussed this topic earlier, and that's a problem that I'm looking into right now, and there are different options. So, I mean, for a grid expansion, you can assume a software, no retrofit, either threshold or line inductor. You can imagine a scenario only software retrofit where you adapt the threshold, or you can imagine both hardware and software retrofit, which is the most complex. So I can't answer your question right now. I believe it must be possible to design the line inductor already anticipating a future extension such that you maybe only need to adapt the threshold and don't have to put a new line inductor.
Thank you very much. And then we have a question from Christopher Sporon. Is the different simulated faults in RTDS applied for both strong and weak grid network nodes onshore that have higher parent power and relatively lower parent power? And is protection action coordination between that is backup protections and controlled protective actions taken into consideration or in the report's conclusion?
Yes. So the first question was the different AC site behavior, and we have not varied that, but we have investigated different systems. So, for example, I mean, the system we investigated with the IEDs in the loop and the real-time study in Scotland is basically the same as on page 22, figure 4.1, and there we have 2 onshore converters with a 2.5 or 15 short circuit ratio. So that's the one is 2.5, the other one is 15. So that's covered, but we did not vary that systematically in our testing. And the second question, could you repeat that, please?
Is protection action coordination between, that is, backup protections and controlled protective actions taken into consideration of the report's conclusion?
That's taken into consideration, not in my reports, but if you look into the related publication, what is it? Related publication number 3 on backup protection, that's taken into account. And then there is another publication that is currently submitted, related publication number 1, where the control impact and then the starting up of the grid is taken into account.
Thank you. I hope I will be able to phrase this one. Is loss of telecom communication between HVDC stations test performed when faults is applied, that is pole differential protection and cable fault protection? So you will see how the different station-wise protection will act respectively, as there is consequently no FOSTA signals available in algorithm conditions, logics, etc., as a condition in the thesis.
So I'm not sure if I can grasp the whole question. If I don't answer your question, please drop me an email later. But in the scope of this thesis, I looked only into single-ended fault detection, and all the studies were considering that. So I did not investigate also link with the remote line and in that scope. But please drop me an email if you want to discuss further.
Thank you very much. And then I just have 2 short questions, and then we wrap up. Is there any limitation about sampling time in this project?
We didn't have specifications for sampling times, so the IED is sampled at 50 kilohertz. That value was chosen because it's based on previous publications on literature suggesting that as a minimum requirement. And I mean, that's how it is in the open source prototype. You can change it. Yeah, I guess that's all I can say right now. And then obviously all the simulations need higher sampling, so you can capture the traveling waves accordingly.
And just a short last question then. With respect to the variation of fault resistance in reality, how can it affect your margins?
The higher fault resistance will result in a bit dampened signal, such that the signal might not be so strong that you want to detect. So as such, the margin is a design parameter that I want the system to fulfill. And for that, I have to take into account the fault resistance as well. So I, for example, take the worst case such that I get a dampened fault detection signal, and then I design the system such that the margins are fulfilled for that case. But the fault resistance does not have an impact immediately on the margin. I mean, that's a fixed parameter that I input into the design.
All right, thank you very much, Ilka. With this last question, it's time for me to close the public defense of your thesis. On behalf of KTH, I would like to thank you. I would like to thank the opponent and the members of the grading committee for your contribution to this, I must say, very successful public defense of a PhD thesis here at KTH. Thank you very much, everyone. It's now time for the grading committee to meet. And that means that the Staffan, I think, will open up the Zoom room for the grading committee. And you will have your meeting, and we will have this webinar going on. However, I will mute us from this room, so you have to be a bit observant. But you will have your Zoom meeting in another room, and then you will come back into this physical room, and we will announce the decision of the grading committee once they have had their meeting. Very welcome back. We have had this room muted for some time, so let's just shout and say that now the grading committee is ready to present their decision on this public defense. Who is chairman?
And I am the one that is going to give the news to Ilka.
Well,
I mean, Ilka, as you can understand, it has been a long discussion. There were a lot of opinions. It was more on how to sign the paper, not about your work. I think that everyone agreed that you've done an excellent work, and we are happy to announce that you have passed. So now you are a doctor. So congratulations.
Thank you very much. Normally this is a very big this is a very big event, of course, and from KTH, first of all, we would like to congratulate you to the new doctor, the PhD here at KTH. Congratulations, and we would like to convey these flowers to you. Congratulations. And I know that Hansi also has some more things to bring along.
On behalf of the School of Electrical Engineering and Computer Science, we want to give you a diploma.
Thank you, Hansi.
And also a small gift from the school. And then your colleagues at the department also would like to give you a gift.
Thank you.
And there will also be some electronic gift cards, which you will receive later on. So,
Thank you so much.
Congratulations.
Normally Hansi sings a song here, but I know that the synchronization and the sound on the internet will not make...
Hej hå, det gjorde hon fan så bra. En skål ut i botten för henne vi tar.
Thank you very much for attending this public defense. I will end the webinar in just a few seconds. Congratulations again, Ilka Jahn, and thank you very much for your contributions and your active opposition and your activity in the grading committee also. Thank you very much, everyone, and goodbye for today.
Thank you.
Congratulations.
Thank you.
Yeah, where are you?
Congratulations and bye-bye.
Bye-bye.
Well done, Ilka. Congratulations, Dr. Jahn.
The document is still being circulated.